Okay, next topic is trajectory planning. So we're getting very close to the end. We need to discuss now how to generate motion for our robot. And this goes under the terms of trajectories because this motion is composed by geometric components and by timing components. And we will see that we can plan this motion in the joint space or in the Cartesian space. And there are many things in common and some slight difference. This is why we have 2 blocks of slides on these topics. But many things that I will say on one side can be applied as well on the other side, except for a few things that I will point out. And after these topics, we will conclude with one big chapter on kinematic control, and this will conclude our course. So trajectory planning. So let's look at this block to understand where we are. So we have the robot interacting with the environment or moving in the environment, and the robot will be controlled by some commands, and we will see how to do this, at least in the simple cases. We have described whatever we need to know about the robot, its geometry, direct kinematics, inverse kinematics, representation of orientation, minimal, differential kinematics, Jacobian, geometric, analytic, inversion, and so on. Now it's over, okay? Now, when we command the robot for doing things, then we recognize what's going on using internal sensing from the robot or external sensors that look at the environment and where the robot is, okay? And this is fed back to other components in different ways. But the whole chain of activities starts from the task that the robot needs to do. For instance, the robot should pick an object on the conveyor belt and put it into a bin. So this is the task, and maybe recognizing which object to pick and which not, and so on. So at the highest level, there should be some generator of elementary frames associated to this task. And this is part of the task planner. This could be automatic if we are reasoning about the environment and whatever mission the robot needs to complete, or it's just part of the operators specifying that where it should go and where it should place the objects. Okay? Now, the task planner is the input for the trajectory planner. Why? Because just giving frame here and there, it's not enough to specify the motion of the robot. The robot may go from one frame to the other with its end effector in many different ways. So we have to specify a trajectory, and this is the task of the trajectory planner. So the input is clear. What is the output? The output will be references for the control. So the control law takes very distributed values in times, not just seldom values, and uses this for imposing the command to the robot. Okay, so the trajectory planner is kind of a core of these 3 steps: planning the task, then the trajectory, then controlling the motion along this trajectory. Okay? So in this context, we will focus on this specific problem. Of course, there is more than this, but this is enough for describing many interesting things. So we start with the output of the task planner as a sequence of poses in the Cartesian space for the end effector, or sequence of configuration of the robot. Because if I'm saying that the end effector should pick up something here, I can specify just frame of the end effector here, or I fully specify the configuration associated to this. This is a matter of how I learn to do this, how I teach the robot to do this. Okay? By the way, and I'm saying it a couple of times and then removing this observation, many things can be associated also to force exchanges. Because I can say you should be there with this orientation, so I'm specifying a pose for the end effector frame. And in addition, the force along one of the three directions should be equal to whatever, or should go from 0 to 10 Newton meters going along a ramp. So I'm touching and imposing a higher force over time. So I can specify trajectory in the same way also for force component. Okay, having this in mind, in the back of our mind, we will remove force from the pictures. So this is the input, and this is the output of the trajectory planner. So a rather continuous, or if discrete, very high frequency sequence of points as reference for the controller. Okay? So how do we do this in a standard robotic environment? So this is a typical procedure. So we define essentially Cartesian poses, so position orientation, using the teach box. So moving the robot, bringing the end effector to where we think things should be picked up and or placed or whatever, and then storing this information. Okay? By the way, this information is not only stored at the Cartesian level. When you do this teaching, the robot knows also the configuration that you have reached. And if you don't like this configuration, so for instance the robot is there but with elbow up, you will move the joints and then bring the robot in the same pose but with the elbow down. So when I'm storing the pose, in fact I'm storing the configuration. So there is no inverse kinematic problem when I'm moving directly with a joystick the robot. Okay? It's automatically solved. But in general it may be not. And then once I've learned a sequence of such poses and or joint space configuration, I can program some velocity for moving from one to the other. And I can decide if to go straight in Cartesian path or in the joint space at maximum speed or medium speed or very slow. Typically an end user which does not interact in the detail of the trajectory planner of the robot controller just gives a percentage in terms of max, so that it doesn't make a mistake to write 1,000 meters per second and then something strange happens. Okay? Now, once this is built, there's a micro-interpolator inside the controller that generates a sequence out of this general description, very qualitative, no mathematics apparently, so to have the references in the joint space for the actuators and for the controllers. Plus you can do more things. For instance, I can teach 4 points for the end effectors, A, B, C, D. Now this is on the plane, but could be in space. And then when I specify a velocity from A to B and B to C, C to D, I may specify to stop in B, C, D, and then in A, and then cycle, or to do what is called overfly. So while moving at constant speed along this path, when I'm entering a final region around the final point, I'm starting to process the next instruction so that he overflies the point without stopping and goes to the next. Of course, I'm doing this if I program this point BC intermediate just to avoid some dangerous obstacle. If I want to really go to B, I have to go there and stop. So this is an option that I can. Then there are other changes that we can do, sensor-driven stop. So I could say, okay, do this and have a cycle until sensor input of a channel, digital channel or analog channel 3 goes up, and then you stop, okay? Or you branch your program and you go to a different place. Or you can specify the 3 points and then just give an instruction saying go on a circle passing through these 3 Cartesian points, and there's always a unique circle provided that the 3 points are not aligned, okay? and so on. So there are additional features that the robot may come equipped with. But you see that if you just observe as an end user of low technical competence this, it's really first generation language, where we move the robot and then we have a skeleton of a program and we just add numbers as parameters. So it's a semi-manual programming. And moreover, if this is not accompanied by a simulation of what's going on, an offline simulation, you don't know what's really will happen in between one pose to the next one, okay? So you have a limited visualization of motion. This is why, if we want really to design, to be able to do this planning, trajectory planning in a smart way, we need to give a mathematical formalization to the trajectories which will be generated. Okay, and this is what we will do with some example. The first concept is, as I introduced it, I remember in the first lecture already, that for us a trajectory, for robots, a trajectory, again, motion or interaction force, but then forget about interaction force, it's a combination of a geometric path and a timing law, okay? And this separation is very important. Again, sometimes it's not so relevant and then you can just define a function of time. But most of the cases, it's better to specify motion as a function of some scalar parameters. And then these scalar parameters, which describes the geometry along the path, will be given a time dependence, which is the timing law. So the idea is the following. Suppose that you have a Cartesian path. So the task planner provides point A and point B. Now forget about orientation, just talk about position. So this is the output of the task planner and is the input to the trajectory planner. Now the trajectory planner had to interpolate these 2 points, and it can be done with a straight line or with the arc of a circle or with whatever path, okay? So this path is described, these are the 3 coordinates in space, by the 3 coordinates px, py, pz of this position p of the end effector as a function of a parameters that goes from 0 to some maximum value, let's say S max. When S is 0, I'm at the initial point. When S increases, I'm tracing this path until S max, and I will be in B. Okay? Now, how fast do I go? Do I stop? Do I reverse? Nothing is said. It's just the geometrics of the path described by this. Okay? Parameterized. And I can use several parameters. I can use the arc length of the path itself, which means that if I'm at S equal 7 centimeters, it means that I'm in a point and the length of the path from start to there is exactly 7 centimeters. Okay? Or I can forget about this association and just say the path parameter is some values that goes from 0, it increases only, and until 1, let's say, and when I'm in 0, I'm here, when I'm in 0.2, I'm here, 0.8, 1, I'm here. Okay, so it has not strictly related with the actual length of this path. Okay, you can do both choices. Now, when does this path becomes a trajectory? When you give also a function s of time. So you're giving, I want to move from rest, 0 velocity, to rest in 2 seconds, which means that I have an interval of 0 t, and the time flows uniformly here. T, capital T is 2 seconds. And then I associate a function of this interval of time to the value of the parameter. If I want to go very fast here, then in few instants of time t, I will trace a lot of the parameter s, and then I will move very fast, and then I want to slow down, which means that the last large remaining interval until the end will be focused in few values of s, okay? And so on and so on. You can imagine all possible flexibility through the time evolution of the parameter with respect to t. Note also that this is three-dimensional if this task is three-dimensional. If I have to include also orientation, I would have had, for instance, an alpha, beta, gamma of s, okay? While this mapping is always scalar. The scalar time to the scalar value of the parameter, okay? This is also a convenient decomposition. So let's consider the most complex transformation of data that we can imagine from data in the Cartesian space given by the task planner, so frames or points, to some very detailed description in the joint space that you provide as reference to your controller, okay? Now, some of this may be skipped, but let's consider all steps for a moment. So I'm starting from the task planner output, which is a sequence of pose points in general, which are also called knots in the Cartesian space. Now, from this few knots, you can generate a continuous interpolating path, okay, in the Cartesian space itself. So you will end up with a Cartesian geometric path which consists of position and or orientation components parameterized by S. Okay? Now you can take this path and do a resampling. So from this path you extract more points than you start from. So pay attention, this sequence is more dense than the original output of the task planner. Otherwise, I mean, you're doing the same thing. You're resampling the same object. Why are you doing this? Because you want to be more fine. Okay? So from this continuous geometric path, you do path sampling, and for each pose out of this Cartesian path, you do kinematic inversion. So you generate a knot in the joint space, okay? So you have a sequence of knots in the joint space, and now these are separated because you have not inverted any possible point from the Cartesian space. You have just selected some points. Now you have to join these knots in the joint space, so now you do an interpolation in joint space. And the function that it interpolates can be parameterized by a different parameters, but I'm just calling it lambda. It could be called S again, but just to distinguish it from the previous one. Okay? And so you end up with a geometric path parameterized in the joint space. Okay? So it's a long story. Not always you need to do all the steps. You may start with a sequence of knots in the joint space, so you need to just do this. In very few cases, you don't have to do this path, geometric path sampling, and then reinterpolation, because you may have an analytic inversion for very simple path in the Cartesian space, very simple robot. You can just skip and have an explicit function, directly a geometric path in the joint space. So, which means you are using an analytic form for the inversion, for the inverse kinematics. Okay? Now, there are other things. It's not just this transformation. The main thing is obstacle avoidance. When you have a pose here and a pose here, and there's a wall in between, of course, I mean, connecting it's meaningless. You have to go around the wall. So you may need to add an extra Cartesian knot, and so to avoid the wall in the Cartesian space, before transferring everything into the joint space. In the joint space, the other consideration which is important in this planning, at this planning stage, is what you compute offline and what you compute online. So whatever can be done in advance and whatever needs to be executed online So for instance, if you rely on a Cartesian planning, since motion is always executed in the joint space with your actuators, at runtime you will have to invert things. So you have to do more computation. If you invert the trajectory from the Cartesian space to the joint space once for all, offline, then the controller needs just to check the error with respect to the joint trajectory, so you don't have to invert things in real time, okay? But you have lost control on what's really happening in the Cartesian space. So if a sensor tells you that you're getting closer to some unexpected obstacle, you have to modify your joint trajectory without knowing exactly what will happen to the Cartesian end effector trajectory. So it would be better to keep a Cartesian trajectory which can be treated like an elastic bundle and stretch in one side or the other side, okay? So there are all these things that make it worth to consider planning both in the joint space or in the Cartesian space, depending on visibility and computational load in real time. So let's do one simple example using the powerful PowerPoint. So let's have this as a starting task. So the task planner has said, okay, the end effector should go to A, then B, then C, and then again to A, B, C. Now I have to generate trajectories. So the first step would be to interpolate in the Cartesian space these 3 knots, okay? It could be straight lines, but remember, if you go in straight line from A to B and from B to C and from C to A, then unless you do overfly of the intermediate point B and C, and you may not be allowed to do overfly because you really have to be in B and C, at least for one instant, then you're forced to stop in this point. Why is that? Because if you're moving from A to B in straight line, when you reach B, you have a velocity pointing in that direction, and all of a sudden you have to switch velocity to the next point, and this jump in the planning of velocity is not really nice, like we have seen before. So you're forced to reach B, stop in B, and then restart from 0 velocity pointing towards C, which will make the whole cycle longer. So straight line are apparently the most direct way for going to A to B, but then in terms of timing, you may need more time to execute them. Okay, so the minimum distance is not really the minimum time in these cases. So for this example, I decided let's do a circle. It may not be the best, but just for illustration. Okay, before doing this, I sketch here what happens in the joint space. So I know that for point A, point B, point C, for this robot, hopefully they are all within the workspace, I can associate some inverse kinematic solution. Actually, more than one. Okay, but now I take one for each point. So I have a value for Q1, Q2, Q3 associated to the Cartesian knot A, and similarly for a Cartesian knot B, and similarly for C. Now, it makes sense here, if you have chosen for this robot, this may be an articulated 3R robot, it may have, in the regular case, 4 inverse kinematic solution. Okay, because I would have elbow down, elbow up, and then front facing, or elbow down, back facing. Okay. Now, if I choose one of the 4 for this, typically I would like to keep this also, this type of inverse kinematic solution also for the next point. Because I know that otherwise I would have typically go through a singularity for change the type of inverse kinematic solution. And this may create some problems. Okay? So now I do the interpolation. For instance, this circle, and this will be P of S. Okay, going from A, B, C, and then generating some Cartesian path I may like it or not, but it's really easy to visualize what's going on in the Cartesian space. And now this is not enough, because up to now in the joint space I have only very rare knots. So what I do, I will oversample this Cartesian path. So take a lot of points, including A, B, C. And now I will invert those points in the Cartesian, in the joint space. So now I have several points, much more than the 3 points that I started with, still to be interpolated. Even if I had an interpolation in the Cartesian space, I have only discrete points at this stage in the joint space. So I may interpolate it with some function, polynomials, or linear path in the segmented linear path in the joint space. Again, not good, because this would mean that joint velocity would either jump or needs to come to 0 at each knots in order to not have this discontinuity. So it's a smoother version, and I have Q of lambda, which means for each component Q1 of lambda, Q2 of lambda, Q3 of lambda, with the same lambda. Okay? Now, I've talked about velocity, but in fact there is not yet a timing here, because I'm generating a path in the joint space, and now I have to give a timing to lambda. Okay? So I'm not saying, even if I see, let's say, I'm saying I'm starting at rest in A. Where do I see that I'm starting at rest in A? I don't see it anywhere. In A, I see a tangent to the path in the Cartesian space. And along this tangent, I may move with 0 initial speed or with large speed. So I need still to give a timing to this. And similarly, here, if I look at the Q point, the 3 component, I see here some tangent. But in fact, if I look at in a 3-dimensional configuration space, this point corresponding to the point A will have a path with its tangent. So I have only tangents to path in the Cartesian space or in the joint space. I don't have still a timing, so I cannot speak strictly about velocity. I can speak of derivative with respect to the path parameter, not with respect to the time parameter. Okay? So bear with me if sometimes I say velocity instead of tangent to the path. And it depends on the context, again. Okay, so a few general considerations. What is better? Now we have seen all the steps. Cartesian space, more direct visualization. So you can guarantee obstacle avoidance, at least for the end effector. This does not mean that the rest of the arm will not hit obstacles. And in fact, this is the main issue. For easy cases, when the workspace of the robot is not crowded with obstacles, then avoiding it with the end effector and trying to keep the arm close to the base will avoid collision. But if the robot has to enter into some car body, so the end effector may be free of collision, but then you hit with some part of the arm against the rest of the car body, so you have still a problem. So Cartesian is not enough in general. And detailed method for do what is called motion planning, so generate a motion for a robot, no matter how many joints it has, no matter if it's fixed based or mobile based, in a 3D environment crowded with obstacles is a very tough problem. It's an NP problem, so non-polynomial solution in time. And some methods will be addressed in the course of Professor Oriolo, Autonomous and Mobile Robotics. Okay. Here we are just considering trajectory planning with some easy obstacle avoidance, which means that we have 1, 2 obstacles placed in a non-tremendous way, so that the task planner, just by adding some intermediate via points, can avoid collision. Okay? So in Cartesian space, in this sense, is simpler. And then you can see lack of wandering. What do I mean by wandering? It means that if I have 1, 2, 3 points, and I'm interpolating no matter how, I can decide what happened between one point and the other. I want to go in straight line or along a circle, but certainly I will not generate some interpolating path that goes up and down like a seesaw or whatever. Okay? While if I'm doing interpolation of very rare point in the joint space, what happens in between, even if there's a regular interpolation in the joint space, due to the nonlinearity of the direct kinematic, I may go around the points A, B, C in an unpredictable way. Okay? So there is this risk of wandering out of a natural motion. Okay? And overshooting, for instance, on final destination. Overshooting means that if I have to go from this point A to this point B on the top of this table, and I'm inverting this into the joint space, and then I'm interpolating in a bad way in the joint space, the results could be a motion that goes there and then goes a little bit under and then goes back. So it will hit the table, while I would like to confine my Cartesian motion between the initial point and the surface of the table. Okay? This would be an overshooting, which is a type of wandering which I want to avoid at the level of planning of path and trajectories. Okay? On the other hand, the joint space is not so bad at all because it does not lead on-line kinematic inversion. Because once I have defined my reference in the joint space, I have my sensor in the joint space. I can compare the position of the joints with what they should be and control the robot in this way. So inversion of the Jacobian is no longer needed, which means that if I have a trajectory in the joint space, the trajectory can also cross a singularity and nothing happens. Why? Because crossing the singularity is critical only if I'm inverting the Jacobian. So I'm taking something in the Cartesian space and inverting in real time in the joint space. If I've done this offline, and I've already taken care of possible crossing of singularity with nice numerical technique offline, online, nothing happens. Once I live in the joint space, I can do whatever I wish. Kinematic singularity are out of discussion. Okay? Which means that you can also fold your robot crossing exactly this point. Probably you will do something like this, but you can cross this point in the joint space without any problem. So you can cross Q2 equal pi and nothing happens because you're not inverting the Jacobian. But if you're forcing a linear path in the Cartesian space and the linear path is crossing the origin in this case, and you're inverting incrementally your motion in the Cartesian space, then when you're getting closer to that point, you will have the explosion of joint velocity like we mentioned. So you see that there are pros and cons of both things. Better visualization in Cartesian space, easy, less computation, and no problem of singularity when you have a trajectory reference defined in the joint space. Then there are other things. I've mentioned before, I need to invert just the pose in the example that we have made with the circle. We had A, B, C, and then the knots. This needs to be inverted. But of course, there's not only position or pose or orientation, there is also the possibility of having specified some Cartesian velocities. And then in that configuration, I need to invert also the velocity mapping so that the joint motion has the right velocity that guarantees also the velocity at the end effector level. Same for acceleration. So sometimes in this inversion problem, it carries on not only the geometric path, but also the timing law in terms of q dot and q double dot, or in terms of variation of q with respect to the parameter s and double variation of q with respect to the parameter s twice, which are geometric quantities. So tangent to the path and curvature of the path needs to be inverted from the Cartesian space to the joint space so that we have boundary condition for the joint path to be used that are coming from the Cartesian space. So pay attention here. Now I'm writing in terms of time, but the same may be written in terms of derivative with respect to the parameter. Then I have another problem. If I have a redundant robot for the task, I have an infinite number of solutions. How do I pick out of them when I'm doing this inversion? Okay. And finally, even if I would prefer to do the inversion offline and so to work with joint trajectories, sometimes the task itself needs some sensor-based correction in real time, so that I have to I cannot define offline the whole trajectory, and I cannot even define offline a trajectory in the joint space, nor in the Cartesian space. So I need to be sensor-driven. So I need only to specify increment depending on what my sensor are telling me to do. Typical case, I have a robot moving like the one that you've seen in the demonstration in the lab, doing a task by itself, and then a human enters the workspace and you want to have coexistence. So the robot needs to change its motion depending on the distance between the robot and the human. So this is something that can be only computed in real time, because you cannot predict what the human will do. Okay. Then as soon as distance increases, the robot safely recovers its original task that has been planned offline. But all this transient implies that you have only a local planning decision, instantaneous, as fast as possible, with some constraint to be satisfied. So again, what kind of path, no matter if you're in the joint space or in the Cartesian space, you have multiple decisions, so linear path in the Cartesian or in the joint space, or a circular, or some polynomial, or some exponential function of S, and so on. And then you have the timing law. Now, about the timing law, okay, just one comment first. Sometimes you may wish to parameterize your trajectory with the natural time parameter. It's perfectly feasible. This means that you're no longer separating path from time. So one possible choice of S of t is t. Okay, so this is a sub case. So about the timing, how do you choose the timing? Well, there are several considerations that you need to take into account. First of all, task specification. For instance, you need to stop in some point, because you need to stop and wait for something to happen and then grab something. Or you need to stay there and do a technological operation like laser cutting for 20 milliseconds. So there is a timing constraint, so you cannot go through without stopping for 20 milliseconds, otherwise the laser cutting will be not completed. Okay? And you cannot even stay too long, because otherwise you will melt everything. So the timing is important, and it is connected to the task itself. The other thing are constraints in the joint space or in the actuator space, or even in the task space. For instance, I'm carrying something, like a tablet for a waiter, and I cannot go too fast, because otherwise what is on top of my tablet will fall down because of acceleration. So I have a constraint in the task space. And then I have constraint in the joint space where the actuator is here. We know that the actuator cannot provide more than a certain torque, and not even more than a certain speed. Also because the torque is enhanced by the presence of reduction. The speed is reduced by the presence of reduction. So I have this limit to be satisfied. And when I'm planning a trajectory, for the same geometry of the path, I need to scale down things, because I have to recover in time my constraint. Okay, acceleration, velocity, Cartesian or joint that they are. And finally, if I can choose something, I can also pursue some optimality. If everything is fine, I have enough torque in my motors, and I do 10,000 times the same task, well, I may decide to do the execution so that I use at best my maximum capability, so that I do in minimum time this cycle. And even if I can improve 10% the total time for one cycle, repeated by 10,000, this will save time, which means that I can produce more, or I can just decide to stop at the end and save energy, not activating the robot for a while, and so on and so on. So there are many optimality conditions that can be considered. Now, look at this simple mathematics. When I'm writing, for instance, this is path parameters in the Cartesian space with the timing law, but the same holds for the joint space. So when I'm writing p dot of time, so a velocity actually, but p is a function of s and s is a function of time. I do change of derivation. So this is derivative of p with respect to s, which is also often written as p prime, so with respect to the geometric parameter, and then of s with respect to time, and this is a speed. What about the second derivative? This is an acceleration because it's a derivative with respect to time, but if I take this and I differentiate with respect to time, I will have a product, so one is differentiated, the other not, and vice versa. So I will have dp ds, another derivative with respect to time of s, so s double dot, and then this with respect to time, which means dp twice with respect to s 2 times, and then s with respect to time. So s dot times s dot, so I have a s dot square appearing here. Okay? And you can recognize that if this is the velocity, this velocity is made by the tangent vector, dp dvs is the tangent to the path, times a scalar, which means how fast I'm going along the tangent. So if I do this here, and I look at the acceleration, I recognize the same vector here, and then another vector here. These are scalar, but these are vectors. And this vector is the tangent. So this is something else. In fact, in this acceleration, I can decompose in this way the tangential acceleration and the centrifugal acceleration. Okay? Especially if s is the arc length parameter. Otherwise, this is not true. Okay? There is some more complex formula for obtaining. But you can immediately see that if I'm moving at constant speed, which means that s double dot is 0, s dot is constant, I may still have different acceleration if this changes. In fact, if I'm moving at constant speed along a circle, I have s double dot is 0. But this is non-zero, and you need some centripetal acceleration to stay on the circle. Otherwise, you would go along the tangent. And this is given by this. So for going at constant speed along a circle, you need acceleration, which is the acceleration needed to change direction, not to increase the speed or decrease speed along the tangent to the path. Okay? And this is all embedded in this type of formulation. So again, what are the types? We have said classify trajectory Cartesian or joint space. Task type, if I have to go from one point to another point, and that's it, and then move again, so point-to-point motion, or interpolate multiple points or knots, how we call it. Some time of continuity in terms of derivative in space or time. The fact that I can concatenate elementary motion. For instance, the overfly is a concatenation of linear segments. So I'm going from A to B, B to C, so point to point, point to point. But in fact, in the intermediate point, I'm concatenating the two linear paths, so overflying the intermediate point. This is concatenation. Then the geometry may be rectilinear, of course, in the Cartesian or joint space, polynomial, and whatever you can imagine in terms of function of a parameter. And then the timing law. Timing law, there are, again, several possibilities. we will explore one case which is very important, which is trapezoidal in speed, I would say, not in velocity. Okay? So that the profile of S dot is a trapezoid, which means that the acceleration is at a constant level, then goes to 0, and you cruise at constant speed, and then it goes to negative, and then you decrease velocity to stop. So it's a rest-to-rest time profile. Or you may eliminate the cruising part, so you just increase velocity linearly, reach a peak, and then decrease it to 0, which means that the acceleration is typically it's maximum positive and then maximum negative, so it's a bang-bang acceleration. This profile is also called bang-coast-bang in acceleration, because when the cruise velocity is constant, the acceleration is 0, so you go from maximum acceleration, 0 acceleration, minimum acceleration, or maximum deceleration if you wish. Or it could be a polynomial function of time. Just like here, you may have a polynomial function, where is it? Here, of S as a parameter, and then S itself is a polynomial function, maybe a different degree of time. They are two separate things, although they are both polynomials. And last but not least, this is very important, the fact that the whole motion may be coordinated or not. That means that each component, if it's coordinated, if each component starts at the same time and ends at the same time. Now, these components may be a Cartesian component or a joint space component. In the Cartesian, I mean, the most natural thing is to have coordinated motion, because when we move our arm, we usually do coordinated motion, no matter if we do it in Cartesian space or we do it thinking of our joint. Actually, we always control Cartesian motion, but we are moving in the joint space. This is learned from where we were child, moving our legs and arms. So we do coordinated motion, which is more natural, which means that you need only a single timing law for all coordinates, because this will give the start time and the end time for all the possible displacement. Okay? In some very simple cases, mostly in the joint space, you could do independent motion of the joint, which would mean for my arm, for instance, if I need to go from here to there, which means that this joint needs to do 90 degrees, and this joint needs to do 90 degrees, because both together, coordinated is like this. If I say first move joint 1 and then move joint 2, this is the uncoordinated motion. Okay? While the coordinated motion is the natural one. Do both tasks at the same time, same starting and same ending point. So you need a single timing law which spreads to both joints in these cases. Okay? What more? Computational efficiency. How do you actually, if you need to do something online, how do you store the information about the class of trajectory? I just make one example, the one mentioned there. Suppose that you have planned a trajectory which is a 7th degrees polynomial. Okay? So you can now decide this trajectory is 20 seconds long. I need one sample every millisecond, 20 seconds. There are 20,000 samples to be stored and to be recovered at runtime as reference for my controller. What if I store the 7 coefficients of my polynomial, actually 8 coefficients, okay, and then evaluate them in real time while moving. While time goes on, I have the coefficient, I put the time, I put the power to the first second up to the 7th degree, and then I have the next point. So I need to do some operation rather than accessing a table in memory, but memory is 7 numbers, not 20,000. Okay, so there's a trade-off between the two things. The second option, by the way, when I store points in in a table format, then these are already time-stamped, so every millisecond. What if I need some reference in between? I need to do some interpolation between data in the table. While if I have the expression, the second coefficient, I can evaluate this at any time, not really every millisecond. I can decide to evaluate the next point after 2 milliseconds or after half millisecond. It's a computation that I do online. Okay, so this is another important point. Depending on the application, one is preferred to the other. The other thing is, in general, especially for the geometric part, predictability and accuracy. Accuracy means that my computation is accurate enough. I mean, I want to remember those robots should be very accurate. So if I have a function which is sensitive to the truncation to the 4th or 5th or 7th decimal figure, then accuracy will be very poor. Or predictability, it's wandering and overshooting. Here our concepts are a bit mixed, but overshooting is, okay, wandering and overshooting essentially something that I can show in the Cartesian space with a simple figure. So let's make again the example of the table. And suppose that I have 1 point here, 1 point there, and then I need to land here. So overshooting means that you interpolate, and then you may do something like this, which is wrong. While wandering means that between one point and the other, you may do something like this. Okay, which is also not good, because you are expecting some kind of tube around, some motion like this. Okay. So how do you avoid this? Well, it depends on what kind of class of path are you using. You may have chosen the wrong class of path for do this interpolation. Or if really there are other conditions that force you to be so, you need to add many other points so that you can shape better the path. Remember that if you have specified points, on those points you will pass certainly, because you're interpolating them. It's outside that you don't know. So if you increase the rate of points, then you will increase also the accuracy in executing. And then even if you're wandering, well, you cannot do much worse than this. So you remain in a tube around a given path anyway. Flexibility means sometimes you cannot define the whole trajectory. For instance, interpolation of 100 points. You don't have these 100 points. You have 10 points to start with. So you interpolate, and then while you're executing this trajectory, let's say you're reaching the 7th point, the sensor provides you the next 10 points. So how you concatenate this on the fly? So you may have some class of function which are more easily handled in terms of modifying the parameters of this function so that you joined what you had with the next point. So this is flexibility. And continuity, well, in time and space, of course, if I would have given, let's consider again this example. 1 point here, again. So I may say I'm going with linear path. So no overshooting, no wandering. But of course, this is discontinuous in space, and it would be also in time if I decide to move at constant speed. Okay? Unless I start from 0 velocity, then reach a cruise velocity, then I decrease and I stop here, and then I restart and I move at a constant speed, and then I stop, and then again, every time I have a discontinuity in geometry, I have to stop. Okay, so continuity in space and time is important. So typically at least C1, but sometimes you want to have, for instance, continuous acceleration at any point that you're interpolating. So if you're joining different paths or timings, at some knots, you would like that at that knot you preserve some derivative continuity, okay, of first, second, third, whatever, okay? So this gives the full picture. Well, this would start. Well, let's do a couple of more slides, and then let's go in a long weekend. Remember that on Monday there will be no classes. It's a holiday here in Italy. So let's start with some example in the joint space. So we want to generate either directly a trajectory parameterized in time, or separately a path in the joint space parameterized by a parameter lambda, and then give a lambda of time. Now, in the joint space, what is nice is that if you think about the example that we made at the beginning, once we have transformed all the initial data coming from the task planner into knots in the joint space, and we have to interpolate these knots, it is not important if we have one joint, two joints, n joints. The interpolation is the same for any joint. So the problem is decomposed joint by joint. So we will see component-wise examples. And the same applies to each joint, provided that you change the data joint by joint. Okay? So this is simple. Typically, how do we solve the problem? By imposing condition, by choosing a class of path or of trajectories directly, which has enough parameter to satisfy the condition that we want to impose. And we will make some example of boundary conditions. And the typical classes are those listed, in particular polynomials, cubic, quintic, and seventh order polynomial are those that you should be more familiar with. So what are these conditions? They are called boundary conditions, but they are not only at the boundary of the trajectory or of the path. For instance, you can impose interpolation, so passage through given knots. You can impose some initial and final and even some intermediate velocity if you're working in time, or tangent to the path if you're working in space. Similarly, you typically specify you may specify some initial and final acceleration. You want to start with zero acceleration, for instance, and end with zero acceleration. Or arrive with no curvature. Okay? So again, in time or in space. And then you may wish to guarantee some continuity up to some certain order. So you specify a class of function which is intrinsically ck, for instance C2, so continuity of acceleration. So let's start with this example, or just make this example. So suppose that now it's generic joint I of an n degree of freedom robot. So I just drop the I and I consider the scalar. So suppose that I should start at some initial value, let's say 35 degrees for joint 3, at time 0. Why not? I can reset time because this is a point-to-point motion. And I should be at time capital T, let's say 2 seconds, in a certain value Q final, for instance, minus 35 degrees. Okay? Moreover, I would like to start with some initial velocity. Now I'm doing things in time, just for simplicity, not to skip it. So initial velocity, V in, maybe 0, maybe not. Maybe not because I'm coming, this is a segment which is coming from some previous motion, so I want to inherit the same velocity at the beginning, and end up at time t with V final. So I have 4 conditions to be imposed, and if I choose a cubic polynomial in time in this case has 4 coefficients because of degree 0, 1, 2, and 3. So I have enough coefficient to impose my boundary condition. Okay? So I will do this, but I will do this with a small trick. So I'm using a a double normalization. This is the way I call it. I think there is also a name of some researcher that has used this polynomial, but I don't think it's worth giving a name to this. So what do I mean by double normalization? It means that I'm normalizing time. So instead of using t, I'm using tau, which is t over capital T. So that tau goes from 0 to 1, and the original time goes from 0 to capital T. Okay? So I'm normalizing things. So it doesn't matter if I need to do this in 2 seconds or in 20 seconds. I'm solving the same problem. And then I'm just rescaling things. And this is the first normalization. The second normalization is about how much do I need to travel. So I mentioned for 35 degrees to, let's say, minus 40. So I need to travel 75 degrees. Okay? So I just write the delta Q. This could be positive or negative. So Q fine minus Q initial. And then I rewrite my cubic polynomial in this way. Q of tau, not of t, so I'm normalizing time, is Q initial plus the variation delta Q times this double normalized polynomial, which I call Qn of tau. Now, pay attention. Tau goes from 0 to 1, but also this polynomial now needs to go from 0, when time is 0, to 1, when original time t is capital T, or the normalized time tau is 1. Why? Because when it's 1, at the end of the motion, delta Q is Q final minus Q initial, plus Q initial gives Q final. So I'm getting rid of how much time do I need and how much space do I need, and having just a polynomial, this one, with its 4 coefficients, to be defined once forever. Okay? So this is very convenient because you make your independence in the solution from this condition. Now you have to transfer those initial conditions in terms of condition for the 4 coefficients of this doubly normalized polynomial. So when t is 0, tau is 0, and the normalized polynomial should be 0 so that you start from Q initial. Okay, this is easy. So if I do this immediately, I put tau equals 0, then I have only d, and this should be 0, so d disappears. Always. Okay? Then I should start with initial velocity at time 0 v in. So I take the derivative with respect to time of this function. The first is a constant. The second is delta q times the derivative of the rest with respect to time. But I see only tau there. So I should take the derivative with respect to tau, and then this is what I write here, and evaluate it at tau 0, which is time 0. And then I should take into account that the derivative with respect to tau is related to the derivative with respect to t by a factor 1 over t, because tau is t over t. So when I'm taking the derivative with respect to time or respect to tau, there's a factor 1 over t of difference. So this means that this one, and if I do the derivative with respect to tau of that function and evaluate it for tau equals 0, what is left is only the c coefficient. This should be equal to v initial times t and then divided by delta q, which was their factor. Okay? So I'm messaging the boundary condition. And the same thing at the end. This will impose some condition on ABC and on ABC for the time derivative. So I can solve this, or I can show just the solution for the simple case of rest to rest. So when the initial and final velocity needs to be 0, then this is 0 and c is automatically 0. This is again 0, and here c is 0. So I have just to solve a plus b equal 1 and 3a plus 2b equals 0, which gives always this solution. So the final result is a polynomial q of tau which is q in plus delta q, and then minus 2 tau cube plus 3 tau square, with tau t over capital T in 0, 1. Okay? So no matter how much you need to travel, no matter how much time you need to take, this is a rest-to-rest polynomial. It's always like this, with two coefficients which are integers and summing to 1, and then of opposite change. There are nice properties that can be generalized. So don't do this mistake of saying, okay, generate a trajectory which makes 37 degrees in 1.5 seconds. Then you need to solve a set of 4 equations in 4 unknown, and you get out with strange numbers. But these strange numbers are exactly those 3 and minus 2 where you put delta Q here, and when you divide time by capital T. So this is still there, but this number are always fixed. Okay, this is an advantage of using this double normalization. Okay, then we will see each other next Friday. Okay, and promised by this weekend you will get the results and the solution of the homework.